You can't do it, Hex. It's literally impossible.
This makes zero sense. Just block each other and nobody wins.
You cannot do it. It's been mathematically proven.
Okay, then prove it.
Gladly.
Okay, we are going to play a full game of Hex. By the end of the game, I will be eating my words or he is a liar.
He will be eating his words. Okay. Red connects north to south. Blue connects east to east. I'm red, you blue.
And I'm already blocking you. But before we argue about who wins, let's talk about what this board actually is mathematically.
It's a graph. Each cell is a vertex, like that's a vertex, that's another one. Two cells are connected if they share a border, not just a corner, an actual border like that one or that one. So these two cells are connected by an edge because they share an actual border between them.
Interior fields have 6 neighbors. Each cell have 4. And corner fields have 2 or 3, depending on each type of coin.
That's an example of an interior cell. It has 1, 2, 3, 4, 5, 6 neighbors. That's an example of an edge cell. It has 1, 2, 3, 4 neighbors. That's an example of a corner cell. It has 1, 2 neighbors. And that's another example of corner cells. It has 1, 2, 3 neighbors. Now we add 4 super nodes. One on the west, one on the east, one on the north, and one on the south. We connect each super node to all the cells along its border like that and that.
So, winning isn't about physically touching the wall anymore. It's pure graph connectivity. For example, red wins if there is a path from the north supernode to the south supernode through red vertices only.
Which means the big question, can this game do becomes, can a complete coloring of this game have no north-south, red path and no east-east blue path at the same time?
And the answer is no. To prove it, we need one key fact about hexagon.
Look at any interior point in this grid. Any point your cells meet. How many cells meet there?
Exactly 3. The interior angle of a regular hexagon is 120 degrees. 3 times 120 is 360. So they fit perfectly around a point, with nothing left over.
This is called the three-phase property. It is the entire reason this proof works for hexagons and completely falls apart for squares.
On a square grid, 4 cells meet at each point, 90 degrees times 4. That one number, 3 versus 4, is the whole difference between a game that cannot end in a draw and a game that can.
Here's why it matters. When you two color three faces at a point, you can only get 3 versus 0, like that one, 3 red and no blue, or that one, 3 blue and no red, or 2 versus 1, like that one, 2 blue and 1 red, or that one, 2 red and 1 blue. There's no even split.
On a square grid, you can get 2 versus 2 diagonal split, red blue and red blue, around a point. And that single difference breaks everything we are about to show you.
Keep that in mind, Caesars never fall. We'll need that in a second.
First, let's finish this game.
Okay, the game is finished and I beated you.
And this is exactly the moment the Higgs theorem is about. We're going to take this finished board and prove that a draw was never possible.
I'm going to draw the bichromatic edge graph directly on the board. Be with me.
This is where it gets me.
So we finished this bichromatic edge with only one assumption. All the empty cells were filled in as a blue, cells red one, and we needed a complete coloring.
So every single cell is now either red or blue, no empty cells. And we have already drawn the bichromatic edge graph on top. Every edge that separates a red cell from a blue cell is marked.
Now look at any interior vertex, any point you see cells meet. Because of the three-phase property we talked about minute before, you either get 3 versus 0 or the same color, which means 0 bichromatic edges, or 2 versus 1, which means exactly 2 bichromatic edges. Like that one, it's see the same coloring red, so there's no bichromatic edges. Here it's two blue versus one red, so there's two bichromatic edges.
So every interior vertex has degrees 0 or 2. And look at the four corners. At each corner, a red boundary region meets a blue boundary region. So each corner has exactly one bichromatic edge coming out of it.
Again, with a maximum degree 2 and exactly 4 degree 1 vertices can only be a collection of passes and cycles, and 4 degree 1 vertices mean exactly 2 passes, the 4 corners pair up, and we have mini circles.
Now, here is the proof. We start at the northeast corner. Walk along the bichromatic dash we have, keep red on our left and blue on our right.
At every interior vertex, degree 2 means there's exactly one way forward, no branching, no choice, you just follow it, like we are following it now. We come here, there's no options. We have blue and red, so we gotta continue making the red on our left.
At the end, we will end at another corner, either northeast, southeast, or southeast. In our case, we reach the southeast corner. So the red region on the left ran continuously from north all the way to south. And this is our winning path.
So let's follow the ring path. We start at the northeast corner, putting the red on our left and the blue on our right, and follow the line. So it's still red on our left and blue on our right until we get here. It reverses. It looks like red on our right, but it's actually on our left. And we continue. So we continue faster now until we found ourselves reaching the southwest. That's the ring pass, and it had to exist whatever corner the walk terminates at. It tells you exactly who won, and someone always wins. We either terminate at the southwest, which gives the red the win, or terminates at the northeast, which gives the blue the win.
So a draw isn't just unlikely, the structure of the hexagonal grid makes it impossible. So the hex theorem gives us no draw ever, but it has one more concept that John Nash figured out in 1941.
If those are impossible, then by Zermelo theorem, every finite perfect information game is strictly decided. Exactly one player has a forced winning strategy.
Nash proved it's always player one. Suppose player two had a winning strategy. Player one makes one arbitrary move first, then steals the strategy. Plays as they were player two the whole time.
The only difference is player 1 has one extra stone on the board, but in Hex, extra stones of your own color can never hurt you, they can only help you. So player 1 wins, which makes a contradiction. Player 2 never had a winning strategy to begin with.
These proofs have been known for 75 years.
Yet, the standard 11 versus 11 board is still unsolved.
So we know with certainty that player one has a winning strategy.
We just have absolutely no idea what it is.
So was I eating my words?
Yup.
Fair enough.